Hi, everybody. It's Professor Mitchell. Today we're talking about section P3 from the prerequisites chapter having to do with radicals and rational exponents. So you're going to see that radicals come up all the time in trigonometry. They've actually come up already when we talked about the distance formula. Rational exponents don't come up quite as much in trigonometry, but they will come up constantly in calculus. So I want to cover them here just in case you don't see them in your pre-calculus class. So the objectives of this section, we're going to review square roots, simplify certain square root expressions. We're going to use the product rule and the quotient rule. Rationalize denominators, which is a big thing in trigonometry, although I don't necessarily feel that it should be anymore, and you'll hear me rant about that later. And then we'll talk about rational exponents. Okay, so this looks very mathematical, but like with a lot of things in math, it's a very complicated way of talking about something that's pretty simple. Okay, so what this is defining is the square root. So as you know, the square root of a number is a mystery number that when you square that number, you get back the original number. So let me just go right to the example. Okay, we say that 5 is the square root of 25 because 5 is the number that you have to square to get 25. And I added a little note to this because there are actually two numbers that do that, aren't there? The square of 5 is 25. The square of -5 is also 25. But when we say the square root of 25, we're talking about the principal square root. The principal square root is just the non-negative one, all right? I have seen occasionally a student will tell me that the square root of 25 is plus or minus 5. That's not true. It's just 5. Okay. There's a different sort of situation where we have to say plus or minus 5, but it's not this. Okay. All right. So that's all that says. Okay. Then we have a few really easy examples. I thought I fixed that. I spent a lot of time fixing this, actually. Oh, well. Okay, so first, the square root of 81. Let me see what's going to happen when I click this. Okay, well, we're going to get all the problems. Oh, here it is. I just accidentally left the other slide in. That's what I did. The square root of 81. So I need a non-negative number whose square is 81. And, of course, that number is 9. Okay. Next example is the negative square root of 9. So what this is saying to do is to first take the square root of 9, find a mystery number whose square is 9, a mystery non-negative number, and that would be 3, and then apply the negative sign at the end, right? So the negative square root of 9 would be -3. Now, I'm a little surprised at myself. Usually when I talk about the negative square root of 9, the very next thing I talk about is the square root of -9. The square root of -9, if the negative is inside the radical, we say that depending on the situation, sometimes we say that that is not a real number because there is no real number that when you square it, you get -9. You have to go to imaginary numbers for that. And we are not going to go there in this class. We're going to go there in pre-calc. Okay, but one thing I did do, because this is very important, we have the square root of 36 plus the square root of 64. Notice there are two square roots there. So what that's saying to do is take the square root of 36, which is 6, take the square root of 64, which is 8, and then do 6 plus 8. Is 14. Do you see the difference between that example and this one? So what students sometimes want to do, they usually don't try to do this when there are actual numbers there, but when I stick some variables under there, what they want to do is break up that square root. So the point I was trying to make here is that this is not the same thing as this, right? Because for the bottom one, what you have to do is 36 plus 64 is 100, and then the square root of 100 is 10. Okay. Simplifying the square root of a squared. So this is something that we have to do frequently in calculus. The temptation is to say that the square root of a squared is just a. You want to say that the square root and the square just cancel each other out. But actually that's not always true because, and you'll see an example of it, I think, on the next slide. What if a is negative? Okay. When you square a negative number, you get a positive number. And then when you take the square root of a positive number, you get a positive number. All right. So the way to make this so that it always works is to say that the square root of a squared is the absolute value of a. Okay. I'm thinking of a certain situation, especially in Calc 2, where that comes up all the time. We have to be very careful. Okay. So here is an example of that I forgot to animate. Sorry about that. The square root of 5 squared. So to be on the safe side, what you can do is just always put absolute value on the number that's inside, the number that's being squared. So on the one hand, the square root of 5 squared is the absolute value of 5, which is just 5. And you can see that that's correct because 5 squared is 25. The square root of 25 is 5. However, if you do the square root of the square of negative 5, again, these two things are not just going to cancel each other out and leave you negative 5. And that's because the square of negative 5 is 25 still. And the square root of 25 is 5. So you have to put an absolute value on the negative 5. All right, so that brings us to the product rule for square roots. And again, this is chapter P, so the expectation is that you've seen this before. Hopefully somebody has explained to you, why does this work? I know that when I teach Math C, I always do that. So what this is saying is that as long as a and b are non-negative, then the square root of a times b is the same thing as the square root of a times the square root of b. And it also, of course, works the other way around. The square root of a times the square root of b is the square root of a times b. So where does that come up? Let's see. Okay, so the first example of using the product rule to simplify a square root, you might remember that when we talked about the distance formula, we had a very similar situation. So the first question I asked myself is 75 a perfect square? And it's not. So the next best thing is, does 75 have any perfect square factors? And it does, right? 25 is a factor of 75. So what I'm going to do with this, let me turn on my spotlight here. I am going to break the 75 into 25 times 3. Then I'm going to use my product rule to break the square root of 25 times 3 into the square root of 25 times the square root of 3. And the point of that is I can simplify, or I can get rid of the square root sign with square root of 25, right? So the simplest exact form for the square root of 75 is 5 times the square root of 3. Okay. And then sometimes, of course, they throw the alphabet into the mix. So here we have the square root of 5x times the square root of 10x. Okay. So to simplify that one, I am going to use the product rule going in the other direction. Instead of taking one radical and breaking it into 2, I'm going to take 2 and combine it into 1. Okay. So I do 5x times 10x is 50x squared. Okay. And now, bear with me for this part. 50 is, again, not a perfect square, but it does have a factor that's a perfect square. It has a 25. And x squared is also a perfect square. So what I like to say about this is I'm breaking 50x squared into the perfect squares and the leftovers. Leftovers are things that don't even have perfect square factors. So then break it all the way down. The square root of 25 is 5. The square root of x squared is x as long as I know that x is non-negative. So I'm going to deduct 2 points from myself because I just got through telling you that the square root of x squared is the absolute value of x. But I'm the teacher, so I can cheat and say, oh, wait, no, I thought about this already. X has to be non-negative because otherwise the square root of 5x would not make sense. It wouldn't be a real number. Okay. But I still feel better if I say it in the beginning. Okay. So since I know that x has to be non-negative, that means the square root of x squared is just x, and then the square root of 2 is just the square root of 2. Okay, then we have the quotient rule for square roots, which works kind of like the product rule. I'm going to say this a slightly different way now. This is saying that the square root of a quotient is equal to the quotient of the square roots. The quotient of the square roots is equal to the square root of the quotient. These are very special properties. If you think back to the earlier example with the square root is 36 plus the square root of 64, and then we did the square root of 36 plus 64. Those did not come out to be the same thing. And what that was showing you is that there's no such thing as a sum rule for square roots, but there is a product rule and there is a quotient rule. It does work with product and quotient. All right, here are the examples now that I've fixed my animations. First one is the square root of 25/16. Now, this is actually not hard to do without even knowing the quotient rule. You just have to think of a mystery fraction whose square is 25/16. And I think you could come up with that fraction. This is just saying that another way to do it is to do the square root of the top, the square root of the bottom. The square root of 25 is 5. The square root of 16 is 4. Which means that the square root of 25/16 is 5/4. Okay. Next example is a little more complicated. The square root of 150x cubed over the square root of 2x. Okay. So what I'm going to do with that one is I'm going to make it just square root of the whole thing. Okay. All right, so I'm going to put the square root over the whole fraction, and then I'm going to simplify the fraction. 150 divided by 2 is 75. X cubed divided by x is x squared. And now this example is almost exactly the same. Earlier we had a square root of 50x squared. This is almost exactly the same. So break the 75 into 25 times 3 because 25 is a perfect square. And again, I know that x must be non-negative. Otherwise, for example, this thing wouldn't be a real number. Okay. And so since I know that x is non-negative, the square root of x squared has to be x. Okay. So the final answer for this comes out to be 5x times the square root of 3. Okay, that brings us to rationalizing denominators. So rationalizing denominators is a little bit of an outdated, obsolete skill. It kind of harkens back to the old days when people didn't carry around calculators, all right? So when you had an expression like 2 divided by the square root of 3, it used to be a big pain in the neck to get a decimal for that. Now it's easy. You just put it in the calculator. All right. So we really don't have to do as much rationalizing denominators as we, tend to put you through. Mathematics is just like anything else. We tend to, it takes us a little while to catch up with the times. There are situations, though, where you do have to do it, and it is important. So I don't think it's a waste of time. Okay, so what we mean by rationalizing denominators is rewrite the expression so that it has no radical in the denominator. Okay. So we'll talk about the easy example of that right now, which is when you just have a single radical in the denominator. Okay. To get rid of a single radical in the denominator, you multiply the numerator and denominator by the smallest number that produces the square root of a perfect square. And that is a wordy, complicated way of saying this. I'm going to skip over this for a minute. We'll come back to that later. So when you have something like 5 over the square root of 3, all they're saying to do is just multiply the top and the bottom by the square root of 3. 3, this 3 right here, is the smallest number that will create a perfect square over here. 3 times 3 is 9. So a very rough rule of thumb is that when you're trying to get rid of a single square root in the bottom, just multiply the top and the bottom by that same square root. All right. I say it's a very rough rule of thumb because you really should simplify that square root first if needed. All right, but in this case, it's fine. So I'm multiplying the top and the bottom by the square root of 3. That's giving me 5 times the square root of 3 on top. And it's giving me the square root of 9 on the bottom. Of course, the square root of 9 is 3. And so the correct form for this expression is 5 times the square root of 3 over 3.